For the worked example for a closed cross-section, thin-walled cross-section subject to twisting, we're just going to imagine that we have a cantilever, so constructed from a steel box section, which we'll see in a minute. I've given the material properties for steel, so the Young's modulus and the Poisson's ratio are going to be important because we're assuming steel is an isotropic material, and that then allows us to calculate the shear modulus. And obviously we'll be shown the applied loading in the diagram. It's worth noting that all that cantilever really means in this situation is that we have a fixed boundary condition at one end, so that will prevent any translation and any rotation, and then we'll see that we actually just have a loading in the form of a twisting moment acting at the free end. So the steps that we're going to look at, so we're going to calculate the torsion constant of the box section, which is really very straightforward. We're then going to calculate the shear stress due to twisting in the web and also the flange of the section. So these have different thicknesses, so it does mean that they'll have different shear stress values, even though the shear stress across the thickness in both cases is assumed to be the same value. And then finally, we're going to calculate the amount that the free end of the cantilever twists. I'm not actually going to deal with part 2 of the worked example because this is really almost so simple that it should be very, very straightforward to just do in your own private study time. So this is the cross section we have. I'm going to use centerline dimensions throughout. So we have a centerline dimension in terms of the width of 200 millimeters, and we have a depth in terms of the centerline dimension again of 300 millimeters. We have a flange thickness, so that's the top and the bottom flange have a thickness of 12 millimeters, and then finally we have a web thickness of 8 millimeters. So because we know that the shear flow, so the shear flow is the shear stress multiplied by the thickness, so the shear flow is constant around the cross section, we already expect that the shear stress will be larger in the web than it is in the flange. And the loading situation that we've got, so we've got the fixed end here, 10 meter long cantilever, and the loading we're applying is this 8 kilonewton meter twisting moment at the far end here. So I've drawn it as a positive twisting moment, so that means that we're going in the x3 direction. So again, using the right hand screw rule, if I just line my thumb up with the positive x3 direction, then this is what we mean in terms of positive twisting moment. So just going round like that. To calculate the torsion constant J, so we just need to make sure that we're obviously selecting the formula for a closed hollow section, so that's the formula here. The enclosed area that we calculate is going to be based on the centerline dimensions again, so it's just an area with dimensions 200 by 300 millimeters, so you can see that's the calculation for the enclosed area here. In terms of how we deal with the integration going around the perimeter, so starting from any point and going round the perimeter like so, we just need to be mindful of what the thickness is over a particular perimeter length. So essentially all we're doing is we're making sure that as we're in the webs, for example, we're using a thickness of 8 millimeters, and as we're in the flanges here and here, we're using a thickness of 12 millimeters. So that's the calculation here. So we obviously have two of the webs, and their length is 300 millimeters, so divided through by the thickness of the web, which is just 8. And then for the flanges, 2 times their length, so the top and bottom flanges, and obviously divide through by their thickness. So we then just end up with this value, and J as a value just ends up as this. So we can see this is really quite a large value if we just compare it to, say, values of the second moment of area that we've calculated previously when we were looking at resistance to bending moment rather than torsion moment. So to find the shear stress at a particular location, again, we're just using the formula that's developed in the notes. So looking and just making sure that we use the appropriate thickness for the appropriate location. We obviously know the value of the twisting moment that we're applying in this case. So to calculate the value in the web, we just work through. I'm converting everything so that I'm working in newtons and millimeters, so that's why we're multiplying the 8 kilonewton meter twisting moment by 10 to the 6. And obviously the thickness that we're using is the thickness of the web here. And so we end up with really quite a low value for shear stress. So this wouldn't really be too much of a worry for us in design at all. So also checking the shear stress in the flange. So we have a bigger thickness, so we expect it to be lower. Indeed, when we carry out the calculation, we end up with a lower value in the proportion that the flanges, or the thickness rather, of the flanges and the web section are to each other. Again, from a design perspective, this really wouldn't be a worry at all. So the final thing that we're asked to do is calculate the twist at the free end. So the twist we label as phi, and the value that we're interested in is theta. So theta is the rate of twist that we've demonstrated in the notes. And so theta, we can just rearrange this formula here. So T equals GJ theta. So we rearrange the formula and we get theta equals the torsion moment that we've applied divided through by the shear modulus, which we're about to calculate, and obviously also the torsion constant, which we just calculated in the first part of the worked example. So for an isotropic material like steel, the shear modulus is simply calculated this way. So it's a relationship based on the Young's modulus and the Poisson's ratio that we already have. If you watch the worked example, or rather if you go through the notes related to elasticity, you'll see this is demonstrated completely there. And we just end up with a value here of about 79, and it would be 79 times 10 to the 3 megapascals, so basically 79 gigapascals. So using the formula that we developed to find theta, we can find the rate of twist, and I've initially found it in radians, and obviously we can do a little conversion in order to find that. So in radians, I found it in radians per millimeter, based on doing my unit conversions here. And then if we want to find it in a sort of workable unit, we can do it as degrees per meter, just by this conversion here. So to find phi, so that's the total angle of twist at the free end. In this case, we're simply multiplying the rate of twist by the total length of the beam. So I've used, obviously, the value that I've got in terms of degrees per meter. So that's why I'm just multiplying by 10. So you can see we're less than a degree. So again, from a design perspective, this really wouldn't be a problem. And we can just convert that back into radians as well if we so desire.